Am I audible to everyone?
Yes, you are audible, sir.
I think we should start now. Others will join as we start. I hope my screen is visible to everyone. Please, if there is any problem, tell me.
No, sir, it's visible.
Right. So today's session is on dynamic mesh capabilities of OpenFOAM. So I made a PPT. So we'll start with the PPT and then move on to hands-on, the dynamic mesh motion, dynamic mesh capabilities of OpenFOAM. So, so my PPT is visible to you all, you guys. Can you see it?
Yes, Abhishek, we can see.
Okay, so we'll start. So today's and tomorrow's session will be on dynamic mesh in open form. So what we will do in this work, these two session is we will kind of introduce each and every dynamic capability that is there in open form. Not every, but the more or less the most important dynamic mesh things. And we'll run a test case. We'll run free as well as forced vibration of that. And basically, the objective of these two sessions is to get you familiar with the dynamic mesh so that like you can choose the optimum dynamic mesh method for your own problem and then you can deep dive into that particular method. So we'll start. Right. So there are various types of dynamic mesh motion available and mesh libraries in open form. So one of the most common is mesh morphing, in which the node movement without topology means topology change means the mesh is not the the nodal point remains the same, and the topology change means uh, so for the mesh morphing, that is, there is node movement. So mesh kind of distort through as the time moves. But in topology changes, we have additional removal of new cells, and we also have adaptive mesh refinement in which we can like refine certain regions of a mesh, or we can also coarsen the mesh. And we have like other capabilities like overset meshes in which we have multiple overlapping meshes, so we have to interpolate between the two meshes. We have immersed boundary methods, which are basically non-conformal body meshes. And apart from that, we have like generalized grid interface and arbitrary mesh interface capabilities in open form, which are helpful in sliding and rotating and oscillating interfaces. In these cases, you don't have to like deform the mesh, or we don't have to we don't have to like refine the mesh. Without topology change and mesh morphing, we can simply interpolate between the two mesh regions. So this is just an overview of the various methods that are in open form. So like, and for the various methods that are in open form, what kind of deformation of a structure they can handle, what is the computational expense, do they use any kind of mesh to mesh or solid to fluid, any kind of interpolation, and their implementation, like are they easy to implement or hard, or so this is very generalized, so you can't take uh, these low and high to the exact thing. They may vary from problem to problem, but more and less this is what we have, like on an average we can say these things. So for example, for mesh morphing, when the mesh is getting distorted, that we can only have low deformation, because as the deformation grows, the mesh skewness will change very rapidly, and we have to go for the topology change. And computational expensive, it is highly like mildly computational expensive and easy to implement. Then there are topology change, where we have to change the mesh, like add or remove cells, So in those cases, we can like have higher deformation, but computationally it is very expensive, and it is also hard to implement. Then remeshing, that we have to, like, there are topology change and remeshing, there are minor differences that we will discuss ahead. But in remeshing, like, there are certain solvers which, like, we can improve the quality of the mesh in remeshing, but it is not like we can't improve the topology change. So there are differences, we'll discuss it. So it can have high, it can like handle high deformation. It is very computationally high, expensive, and it is hard to implement. Then we have artificial arbitrary mesh interface, MRF and GGI. Then we have overset mesh, and lastly immersed boundary mesh. These overset and immersed boundary meshes are computationally low. We have lesser computation needed for it. And but the immersed boundary method, although it is easy to implement, but like achieving the convergence for complex problem is hard. So like you have a variety. So these are just like general methods. So in between, all these methods, you can add like you can use topology change with GGI. You can use overset mesh method with mesh morphing or topology change. So you can has various combination of these different like meshing capabilities. So for your problem, based on your requirement, you have to decide which dynamic mesh motion uh, method is suitable for you. So once you find a suitable method for you out of these permutation and combination, then you'll move ahead to the more deeper things in it, because when you do dynamic meshing, it is very hard to get convergence, or you usually get lot of coded number problems, mesh quality problems. So you have to go into each and every parameter in a specific method. You have to go a little bit deeper. So these are various methods. So we'll move ahead to the next slide. So the thing is, the various, so these are dynamic FV mesh without topology change. So these are libraries. Like this is the source file libraries. So you can see each and every library is interlinked with each other. So this is ESI version of OpenFOAM, I think 2.3, that is available on internet. The Doxygen is available on internet for that. Now this is with topology change. When the cells are changing, body is also changing. So, but the thing is, one more thing I just forgot, that the methods that are in red in here are only available in either in ESI version or foam extent, or they are not available in foundational version. So these overset, immerse boundary, and this mesh kit solver for remeshing, they are only available in foam extent and ESI versions. So whatever the version you are using, if you want to see the doxin and interdependency of these libraries, you can try this. This is what I found, one of the thread from one of the thread in CFD online, and this is the link for it on the right in the red. So you can just Google it, and you'll find this like this methodology to generate your doxygen from the, like, from where you have installed the your open form. You can go there and you'll find run these commands there, and you can get your doxygen in the real time. First you have to install doxygen, of course. So I am here using OpenFOAM 7 and foam extent 3.2. In my PC I have foam extent 5. So like I use all of these. So like so what whichever version you are using, you just have to like see which are capabilities available and just try this. So if you don't have foam extent, I'll give you test cases, and then later you can install it and test like run the test cases that I'll be giving. So the important thing is in dynamic mesh motion is, for example, let's say when the mesh is getting distorted. So mesh is moving. So we have variable transport governing equation for any variable. So that can be U, V, P, or even temperature. So phi is any random variable. So in Eulerian approach, what we have is, so this is just fundamental of like how the dynamic mesh works at the fundamental level. So let's say we have at the left bottom, we have a material at like lower bottom mesh. and in the next time step it moves to the center mesh. So in Eulerian approach, so the mesh remains the same and the particle kind of moves to the that mesh point. All right, so the material velocity is u and here mesh velocity is 0. But in Lagrangian approach, what we have is like we want to track exactly the part of the material, or that can be like anything. So in this, you can see the point, the left bottom point, mesh points exactly move to the point where the material has moved. So that is velocity of mesh is equal to velocity of material. You can say that is u. But when we have mesh motion as well as, so that is this is typically in arbitrary Lagrangian Eulerian approach. So so the point is here, and you can see on the right, you can see that the mesh has moved and the particle or the material has also moved to the that mesh point. But here, like the particle should be a little bit behind. So here, due to the motion of the mesh, there is an additional velocity that is like in that is in the transport of the material due to the motion of the mesh. So in these cases, so wherever you see dynamic mesh motion, Navier-Stokes equation, in the convection part, in the convection part where the u is, you'll always see u minus u mesh. So this is to adjust the meshing velocity to the transport of any variable. So so there are so the point is to move for the dynamic meshes you have to move the cylinder or whichever the structure you have. So the motion of the cylinder, so you have to you have a motion of a structure, and according to that you are adjusting the nearby mesh. So for that we have a lot of libraries, so dynamics, so which solve these motion. So we have dynamic FB mesh solver, rigid body motion solver, and solid body motion functions. And we also have 6 degree of freedom rigid body motion. So the point is some of these you can see in these are the dynamic mesh files. So some of these are implemented in the dynamic mesh dict, and some of these are applied as a boundary condition. So there are also tricks to like interdependency, tricks to learn the interdependency between various libraries. So first we will go ahead is with mesh morphing. So you can see at the top we have mesh that is made out of block mesh, and you can see the vortex shedding is happening. This is forced oscillation. You can see the mesh is getting deformed with respect to the motion of the cylinder. At the bottom, I have, so the problem with top is you can't have, like if you have 3 or 4 cylinders, making block mesh is very hard, and it can also be, it is hard to implement. So in those cases, we can go with the tetrahedral meshes, and we can have multiple cylinders or multiple structure in it, and then we can apply mesh morphing. So these are the two cases we'll be discussing. All right. So now we'll move to the hands-on part. So first we'll discuss about the mesh morphing. Okay. So we'll learn everything from the test case. We'll run the test case. It will tell us everything about workshop. 1 second. So this is the case that I have already run. Okay. So what do you need for? So we'll do a F302 for form extent, and then we'll form in tutorials. We'll clean the test case. Okay. So for mesh morphing, what do we need? Okay, we'll discuss step by step. So first, we have block mesh dict file. So this is the block mesh dict file in which you can see we have like too many blocks, right? First we have block mesh. So I have parameterized it. I'll be giving, so it took me a lot of time to parameterize the block mesh. So this is basically this case. This is basically the top case. You can see we have block mesh. Then we have a important thing, a dynamic mesh files. All right. So you can see that we are using dynamic FB mesh. Which library? We are using dynamic motion solver FB mesh. And we are using these motion libraries. And the solver name is displacement Laplacian. And we are using this particular methodology, like this particular methodology in this solver. And this is where the particulars of dynamic mesh are like defined. And then for the motion of the cylinder, so this is simple problem for flow over a, so for the motion of the cylinder, we have this point displacement where we are defining cylinder. We are using this library for the most to like give motion to the cylinder. And we have an amplitude of 0.2 and oscillating time period or oscillating frequency of 0.8, that is omega. And initial position is 0, 0, 0 for every, like the cylinder is at 0, 0, 0 in the initial position. So let's first run the block mesh. So we have run the block mesh. What we will do is first let's comment this out and we'll just write anything. Even something else like this. Now in control dict, one more thing, control dict file. Control dict will be, so it is always like suggested to you adjustable runtime, because in dynamic meshes as the mesh changes, the cooler number may go very high because the mesh get distorted and this quality decreases. So it is advisable to always use adjustable runtime. That is adjust time as the mesh with respect to the mesh. Then we have function objects. So these are the function we are using for these are library live forces. So this is used to calculate forces on the cylinder. So you have to give the name of the patch, p name, u name, row. I think these are simple things. You must have learned this through the workshop. Now in FB solution, the extra term that comes is this cell displacement. So for dynamic measure, you have to include this term. All right. And it is always advisable to have at least one outer character, that is 2. And okay, so we should also include this as one. So we should, in dynamic mesh, we should have multiple corrections at each level of the solver. So if you are, so this is the important part. You have to add solver for cell displacement. Now, now we have run the block mesh. Now the solver name is pimple dy form. So we'll try to run it. So you see, I deliberately give a bad name. So what it does is, so it automatically tells me that unknown dynamic FV type this, and valid dynamic mesh types are these. So we have these 18 dynamic mesh libraries or solver that we have, like, so inside these, this is attached dynamic body FB mesh. So now we will go through these and see what are, like, where are these situated in source file. So because I have to OpenFOAM and form extend both, so I usually go through the path of, like, I usually use the graphical user interface. So we go to the source file and we go to there is the dynamic mesh. We go here. Now you see here we have dynamic motion solver FB mesh. So now if you want to see like where this situated is, you can use grep command. All right. So there are a lot of, okay, so it is too many hours. Okay. So there is no need for this command right now, but anyway, this command is useful. So what this does is, so it will give you like each and every address or each and every location where this dynamic FV motion solve dynamic motion solver FV mesh is right written on a file. So so we go to dynamic FV mesh and it says like we have 18 types of dynamic FV mesh types that we have. So you can see that whatever that it is saying, it is these are already here. So we have dynamic body mesh, dynamic box FB mesh, dynamic FB mesh, inkjet. This is what we are using here. That is, this is the library that we are using here. That is dynamic motion solver FB mesh. So if you look into here, deep, you can see, go to that file where a motion. This is a description. So this is the FB mesh library where a motion solver is used to move the mesh. The user specific motion using boundary conditions. So we have to give motion in boundary condition, that is point displacement. So you can't just give motion in the dynamic mesh, which in some cases, in some libraries it is so, but for this particular, so this particular motion library, you have to give in boundary condition, that is point displacement, appropriate motion variable. All right. So now you know that this is the dynamic motion solver FV mesh, and we know where this comes from. Now the next thing is where this motion solver libraries, it is just like calling it. And the next is where this displacement Laplacian is coming from. Okay, so where is this solver situated? We'll look into it. So these are various libraries or various dynamic mesh capability that you can use, like solid body motion and but all of these are with dynamic mesh, like mesh morphing. So these does not include the cases of mesh topology. For mesh topology, it is written here, like you see. So when you go to this dynamic mesh folder, you have direct topo change and motion smoother, motion solver, and you have poly mesh modifiers, poly topo change. All right. And you can see topo changer FB mesh. So these are where the addition and removal of the cells is done. So these topo changer FB mesh means where the topology is changing. Now about this part, I have copied it. So where the solver for the motion of the library or the solver for motion of the mesh, like distortion of the mesh, how it is done. Where is the this solver? So for that, we will do this. Now we will use grep command. You can see it is saying we have to go to mesh motion. Mesh motion. Second. We have to go to the FB motion solver and hold on. We have to go to the mesh motion FB motion solver. Okay. So we are here at dynamic mesh. Dynamic mesh. We have FB motion solver. One second. Yeah, we have to go to my mesh motion, and then we have FB solver mesh, and in that we have displacement and Laplacian. So FB motion solver. Okay, so you see here. So basically in dynamic mesh, we have the change in mesh, we have topology change, and we have like Laplace equation or various equation, partial differential equation, which are governing the motion of the cylinder. So which are situated in mesh motion, which are like these are the level which are governing mesh motion. And this FB motion solver is for the mesh morphing. This mesket motion solvers are for the remeshing part, in which we have to add or remove or maybe improve the quality of the meshes. And these are the motion for the bodies. So this is so like rigid body, this is solid body function, solid body motion functions. And we have also like motion solver for tet motion solver, that is tetrahedral. But for now we'll go for this. You can see FB motion solver. So okay, you can see here that we have different solver based on displacement and based on velocity. Based on displacement, we have displacement FB motion solver, interpolation, Laplacian, SR, SBR stress. So here in this case, we are using displacement Laplacian. Okay. So you can also use the same trick for this also. You can like random write anything, and then you do pimple dy form, and it says what it says, unknown solver type. So selecting in dynamic FV mesh this, but the unknown solver type. What are the solver types we have? We have this radial body function displacement. These are the solver we have. We have Mesquite solvers. So these are the solvers we have, which you can also see here. These are the various motion solver that we have. All right. So here for this problem, we are using this displacement solver, and in this solver also we can provide different diffusivity. If you want to go a little bit deeper into it, we have displacement, and you can look into these. Like you can always, so if you are particularly your problem is this mesh morphing is good for your problem, then you can go like deeper into the various things. But for this workshop, we just go to the introduction. So you can have a look into it. So what we will do is now we'll run. So this case will run. This is for forced oscillation. So I want to just tell you that this oscillating displacement. So how do we give motion to the structure? So for giving motion to the structure, we are giving boundary condition. Okay, we are giving motion in the boundary condition, and we are using this displacement. This is the type as oscillating displacement. So where this is located is you can always see in so mesh motion. So this FB motion solver is for the motion of the mesh. But we have what? We have a patch. So what about giving motion to the patch? These are the motion diffusivity, like inverse displacement you can see here in the code. Yeah, inverse volume, inverse distance, inverse phase distance. So these are for the diffusivity. Now let's back to what I was saying. So how do we give motion to the patch? So these are for the motion of the mesh. For the motion of the patch, we have point patch. So wherever in OpenFOAM you have something like point patch field or something like that, you just like you can say that it is for the motion of the patch, or it's something to do with the patch. So this oscillating displacement we are getting from this point patch field, so which are used to give motion to the patch or the structure. And we are using oscillating displacement, which is this one, oscillating displacement. And now you can like go open the C file, and you can see what are the things it requires. It requires axis, origin, angle, amplitude, and omega. All right. So these are the things that it is required. Sorry, it is angular displacement, but we have oscillating displacement. So it only required three things: amplitude, omega, and value. So amplitude is a vector, and omega is a scalar. So this is how you navigate in the dynamic mesh to see how to, because otherwise you won't be able to judge that either we should put this like motion of the structure in point displacement in the boundary file or in the dynamic mesh. So there are a lot of confusion in this regard. So for that you have to like go to the source file and see how it is like working. Let's see the result. I think this is more enough. So so the thing is mesh morphing with a like like block mesh file or hexahedral meshes is easy. I'll just show you. So let's run it. So you see it is like you can see the vortex shedding. Vortex shedding has begun, and you can see the motion of the mesh also. So this mesh morphing works very good for this kind of mesh, like in which we have hexahedral elements and we have long hexahedral elements. So mesh morphing is good for this. But when we have like a complex body, which is not circular cylinder, it is hard to give this kind of hexahedral element to the whole domain. And in those cases, mesh morphing can like give lot of core number problems, pimple solver problems. So just to see that, what we will do is, so I myself have not tried it. Let's try it. So let's give an amplitude of 1.0 because I want to show you that how the pimple, like how the current number problem looks when the mesh get too much distorted. Give it at least a minute to run. Just we want to see that where it diverges, like when the current number problem begins to come. Okay, so it's not giving any problem. You see, if I run it, it is now moving rapidly as compared to previous one, right? Let's first what do is let's now give it like 3 extreme. So amplitude is 3, like it is too much amplitude. Now even if it is not throwing any Coulomb number problem at this amplitude, means this mesh and this kind of mesh and hexahedral elements are very suitable for this particular problem. That is like VIV of a single cylinder or any cylinder. So if you are able to make hexahedral elements, then it's good. It's working well. We have to see either whether the validation is okay, but the results are physical or not, but it's not diverging. So we'll keep it running. So there is no point in waiting. So the next thing is like tetrahedral mesh. So what you have to do is, so this is tetrahedral mesh. I'll just show you how it looks in mesh. So in tetrahedral mesh, everything is same. There is no change. It's just that you have to make the tetrahedral mesh for flow over standard from some other software. Here I have used Gmesh, and I'll just share the files. So this is the mesh that, so this is the geo file for the Gmesh that I have used. So this is the geo file that I have used to make like tetrahedral mesh for the triangular mesh, because it is 2D. Triangular mesh for the for OpenFOAM, and then what we do is we just do gmesh to form, and that is we do like there is a command gmesh to form. It converts the .msh file of gmesh to the OpenFOAM compatible files, or it converts it into like points, neighboring cells, neighboring faces, like owner cells and neighbor cells. It is just generate the polymesh from this. So if you want, tomorrow I can just show you how to like generate like mesh from Gmesh to OpenFOAM. So this is how it is. There is one thing that I also have confusion about, that why it is giving a patchy velocity field. Validation is okay. I have seen it, like it is, you see little bit of white and patches are there. I don't know why they are. So I have a close look. You can see the vortex shading begins, and you can see the whole mesh morphing for this case. It is not diverging. So in this case, even at very large amplitude, it is not diverging. See, it is way too much displacement. And you see the vortex shading is also changing. So this is a very perfect mesh if you have a single structure, rigid structure, for which you can make a hex mesh. You see, it can handle very large deformation. But I don't think that this can handle such large deformation. So what we will do is form plane to. Now I have this polymesh like separated here. On this is single mesh, you see. So you can do also do like this. 1 second. So this is the MSH file that I have generated for Gmesh. So for to generate, so to generate the polymesh file for this single .msh, what you have is, first you have .geo file. You then generate Gmesh from Gmesh the mesh file in this format, that is .msh, and then you do this. That is the command gmesh to form into single. This is giving me some problem. I think so now let's not go into, because we have limited time. So if you want, we can cover it tomorrow, but for now we have polymesh here. So what we will do is similar to previous, we just do it quickly. We give 3. It is working good for like zero point 0.2 of displacement. What we want to see what happens if we give 3. Like 3 amplitude is very large. Yes. So now what we will do is pimple. So we have copied the polymesh file already. In the polymesh, it is already there. We don't need to run block mesh here, because the file is already there. Tetrahedral mesh. So it is saying patch 0 is not empty type. Okay. Okay, let's see what it is. So okay, so we have to, so this is generated from Gmesh. So we have to like give front and back as empty. All right. Saying top and back is undefined. So the thing is, in geo file we have to define physical surfaces like this, which is our by default it like extract from there. But it is the names are not same. We have to give top and bottom. All right. But when we have like as I already so let's run it. It will keep running. We'll discuss some more things. So so when we have multiple cylinders, let's say 2, 3, 4, 5, 6, or maybe like very complex bodies, it can be like dissection or maybe a complex shape of an maybe a corrugated airfoil. So if we have a corrugated airfoil, we have to go for the snappy hex mesh or we have to go for triangular meshes. In those cases, we can't go with this block mesh. So I have generated a file here which handles two cylinders. I'll just show you. We'll not run it. I'll just show you. See, you can see the vortex shedding happening from the both cylinders and the upstream cylinder is moving. You can see the mesh deformation. All right. So when we have too many structures or very complex structure, block mesh, so tetrahedral meshes or other kind of meshes is way to go. And for my surprise, it is still working, but it is not generating file. It is taking too much time. So I hope you have like the basic idea of mesh morphing. So this is about the mesh morphing. Like how you can use the deformation of the mesh. So these always have its drawbacks. Like you have to at each and every time you have to calculate the how the mesh is getting deformed. You see, the thing is, although it is running, but it is taking way too much time. At larger amplitude, it is taking way too much time. So we had in the source file, we had dynamic mesh, we have dynamic FV mesh. We looked into dynamic motion solver FV mesh. And in the mesh motion, we looked into how the mesh is deformed, what are the various FV motion solvers for the mesh, and in those for those solvers, what are the various diffusivity and what are the various motion to the structure or the motion to the cylinder that we can give. These are the motion that it can handle, right? It is taking too much time because deformation must be very high. That is why. So now, no worry, we will move ahead. So the point is in mesh morphing, we have to like solve the mesh solver. The mesh solver will solve the deformation of the mesh for the whole domain. So that is very time taking and it takes like very computationally high time. And it is not feasible in many cases. For example, multiple structures, complex bodies to have this hexagonal mesh. So there is always so we also have adaptive mesh refinement. We'll discuss later. So the way around like is to use grid generalized grid interface. So if you look here, you see we have given a topological change where as the cylinder is moving up and down, it is adding layers to the top and bottom of the this square. So this is one of the capability of OpenFOAM, that is generalized grid interface, and the little bit advanced version is called AMI, that is arbitrary mesh interface. So we are coupling arbitrary mesh interface with the topology chain, that is adding adding and removing layers. So we'll now next we'll go to this methodology. We'll discuss what are the drawbacks of this, what are the advantages. Advantage is simple. You don't have to solve for the whole domain. You can just solve for a limited domain, and it is computationally not very expensive, and you can use a block mesh. All right. It is taking way too much time. So we'll move ahead. We'll see the result at last. So the point of telling you this is that at some point, if we keep on increasing deformation, or if we have multiple cylinders like 4, 5, or complex body, at some point the mesh morphing will not work, and you will have to move to the other, like topological changes like remeshing, mesh kit solvers, or others. So here we'll move to this topo changer heavy mesh. Okay. So now here we will study. So one more thing that I want to tell you is that so you have tutorials, like we'll go to the tutorials. So now we'll study topo changer heavy mesh, and now in tutorials. Now if you want to see like what are the various test cases that has capability of dynamic mesh motion, you can just simply do this. Mhm. Dynamic mesh dict. Okay, sorry. Now, if you want to look into tutorials like which are the various test cases that are available with dynamic mesh, you can do this. All right, you can use grep command. It will give you all the test cases that are using dynamic FP mesh. Now, what we want to use is we want to use topo changer FP mesh. Okay, so what you can do is you go to form extent. Sorry, you go to the source file, and as I have told you how to navigate. Now you want to study the topo changer FP mesh, and in that you have all these like library that we can use. Like we can dynamic topo changer FV mesh, types of dynamic mesh we can use. So let's say we want to use this one. You just want to test this one. You want to see where this is. All right. In the tutorials, you do this. You copy the name like multi-body topo changer and copy the name and you run it. So you can see with topology change, and that in particular with multi-topo body FP mesh, we have 4 or 5 cases, test cases, and that are in move dynamic mesh, and that are in and also in pimple dy form. All right. So we will go here in tutorials. We will go to the incompressible pimple dy form. You see moving cylinders. All right. You can always copy and paste. So in this, if you go, you can see the dynamic FP mesh types is multi-body topo FP mesh, and these are the various parameters that we will discuss. All right. So basically, it is just to navigate. Then you can copy this your run folder that I have already run. So this is moving cylinders, and if you simply run it, how do you run it? dot slash or run. Okay, this is not going well. So it is saying what? Okay, so the point was I initially run all these cases in form extend 5, but but there is some problem internet issue in my desktop at my lab, so I have to transfer each and every case to the my PC, which is on form extend 3.2. So these things usually happen. So what error it is giving is, if you look at the pimple log file, it is saying everything is okay, like it is every command is running well. At last it is saying keyword divergence, this is undefined in FB schemes. So what we have to do is, like, you can go to this moving cylinder case of the form extent to go to system. You just copy solution and scheme, FB solution, FB schemes, and copy it here. So there are always like changes from different versions. So now we'll run pimple. Now you see it is running. So it will just take a few seconds. Stop it when I just quickly see the results. You see, we have two cylinders, all right, and they're both moving like that. So the best part is here you can have like 10 or 20 cylinders in line. So so if you have flow induced vibration, or if you have forced vibration of multiple bluff bodies, like 4 or 5 in tandem, this is the best approach to go. Like the block mesh will so you can't just generate simple block mesh with mesh morphing for 5 or 6 cylinders in line. That is not like very hard, not possible. So this is a better version of dynamic mesh, better methodology. If you have like 4, 5, or 2 or 3 or multiple cylinders in like inline arrangement. Okay. Now I have generated this for single mesh. So what are the various things that we have here? Okay. So block mesh is there, and it is, so we have, first thing we have a dynamic mesh, then we have a block mesh. So also I have changed this block mesh and I have generalized it. Okay. So I have parameterized a mesh for this also. So this is single mesh. So now the question is, for this topo changer FV mesh, that is multi-body FV mesh, what are the various things that we need? Okay. So first and foremost is, in these type kind of cases, so you see what are the various things that are there. So we have a left side, left side of the domain, and we have the central part, and then we have a right part, and the top of that we have a square section. So we have two interface on the left and right, which are which are like transferring data through the interpolation, and also for the motion of the cylinder over to the middle, like middle square section, or middle part, there is an interpolation of the motions. And so there are like very numerous type of interpolation taking place. All right. So what we have here is, the point is, there are interpolations at the left interface, at right interface, and and overall the total interface at the center. So what are the changes that we have as compared to like normal block mesh? Okay, so as compared to normal block mesh, what we have to do is we have to define each and every block as a we have to give each and every block a name. So for example, the the block at the top of the cylinder one. So this is, so first we have cylinder, okay, and then around like four blocks are showing the first cylinder, and then the square around cylinder is again made by other four blocks, and we are each for each and everyone we are giving name cylinder one. One second. Okay. Now for the block at the top of the this total square mesh, we are giving name C1 BOT. And the bottom we have C1 top, that is cylinder one top, cylinder one bottom. And we have given the front block the name lead square and the tail square. One second. Uh, so the point is, if you are using topo changer FB mesh, you have to assign name to every block for the interpolation sake. For example, at the end of lead square and this C1 top and C1 bottom and cylinder one, we have one interface. On the right, we have another interface, and then the bottom we have another one. Okay. So the okay, so now we'll go here. So you know that in block mesh we have to define which is the cylinder. That is this cylinder one is the whole mesh that is moving. The top of cylinder is C1 top, to bottom of cylinder C1 bot, and then we have leading and tailing squares. Okay. And then in the boundary we have inlet outlet that are basic bottom and top walls. Okay. And we have first cylinder, that is only cylinder, and we have front in, that is, and the type is GGI, that is generalized grid interface, and the shadow patch we have to define for it, that is front out, and it has only one face. So this is like the rightmost part of the leading square and front out. So this is the leftmost part of the inner block, middle block, and it has three faces. That is C1 top, C1 bottom, and the cylinder. And for this, the shadow patch is front in. Similarly, from the tailing tailing block, we have like back in and back out. These are just similar to this. So these are the things you have to define block mesh. In dynamic mesh dict, you have to define bodies. You have to define moving cells. So which are the moving cells? That is cylinder one, the square part, that is the moving cell. And then we have layer faces, which are top layer cylinder one, top layer cylinder, bottom layer cylinder one. And here we are using solid body motion functions. And here we are not giving this as a boundary condition. Here we are implementing it within the dynamic mesh motion live, within the dynamic mesh dict file. So these are the things that you have to understand. So now when we run this simulation, okay, so there are two extra command, that is set batch GGI and set batch motion. So the first, so why we are doing, we have extra commands is first, we are defining the interfaces. The front in and front out, we are defining as a patch. First, for interpolation between the two surfaces, we have to convert these two into a faces. So you see face set front in zone, that is patch to face. So we are converting the patch to face. All right. And in the second, okay. So in the second command, that is set batch motion, it is what is dictating is like throughout the motion of this cylinder, throughout the motion of the cylinder, we see interpolation between square and top and bottom. So in these cases, the mesh which is moving is called as master cells, and mesh which is stationary is called as slave cells. So in these cases, we have to define which is the master cell and which is the slave cell. So for that, for that, this is set batch motion, means we have to define the zones for the motion of the meshes. So we are doing his phase set. We are identifying top layer cylinder 1, and we are doing cell to phase cylinder 1. That is top layers of cylinder 1. All right, then we have cell to phase C1 top, and then we have C1 top. So in these two, we are defining the top layers cylinder 1 master cells. So in all these, so here we have like uh, top layer cylinder 1, top layer cylinder 1, and we have a layer cylinder 1, which is master cells. So for bottom and top, we have to define it like this. All right. So if you are not defining the master cell and slave cell, it will not be able to identify the motion, like which are the cells that we have to give motion to. So you can so you can simply run dot slash all run, but you can also individually do it. Okay, so it is just simple, like what you do is first you run block mesh. Then you have set patch motion. It's not the command. You can always go to run. Yeah, this is the exact command. If you run these commands, so the first command is to convert the patches to faces for interpolation, and the second command is to identify which are the master cells, that is the moving, and which are the slave cell, you can say, which are stationary. And you run it, and then you do pimple dy form. What is saying? Okay, second. Set that motion. Second. Top cylinder 1 for body front cylinder. Okay. So we can always look into this. 1 second. So when you go to the constant folder polymesh, you can see you have some extra sets back in. These are the various things. So it is saying one of the thing is missing. Layering zone, top layer cylinder 1. 1 second. Set to zones. Okay, now so set to zones is now it is running. So we needed to run this. And it is diverging, you see. So this is the case which is diverging. It is saying current number mean and this. The current number mean is this and maximum is this. Velocity magnitude. So there is some error, like These are not straightforward. Test cases was running good, but it is giving us some problem. So the point is you have to identify a perfect combination of the ratio of the meshes between the master, the slave patches, and the interpolation at the front and back interfaces. So you have to do a lot of permutation combination for this. So I have tried some case. So this is the one of the mesh, the fine mesh that I used. Okay, I'll show you the mesh. So this is parameterized mesh that I've used, and this is comparatively fine as compared to the test case, and it is running fine. Like, but after, let me show you. So the point, what I'm trying to say is, if you think that this is like this method is good for your problem, then you can go deep into it. Like you have to try for weeks, like not for months, maybe 2 3 weeks, that which is the perfect combination of the mesh ratio. Right now, if you just look at this, you can see the ratio is not looking good, the right and left and the bottom. So you have to work on it and find the ratio which will not give you an error. Okay. So the point, so it is after this, it is diverging. So if you look and take a closer look, sorry, you can see it is adding layer. The cylinder is going up and it is adding layers. So you see here we have to define the moving cylinders, top and bottom layers, and we also have to define minimum and maximum thickness. All right. Mm, and you see the due to the minimum thickness that we have given, it is adding layers. So as the cylinder is going up, it is adding layers. These are the very small layers. And this adding additional removal of the layers has to be done very carefully. Like, you have to define these values very carefully. All right. So if you are able to get a good optimum, optimum mesh sizes for each block here, you will be able to like get your simulation running. And this is very good for multiple cylinders intending. In initial time step, it is running good, but at larger, as the simulation is progressing, it is giving us some problem. Initially, it is running good. You can see pressure is forming well, but sorry. But as the simulation is progressing, it is giving us problem. Okay. For this topo changer FB mesh, you can have multiple, you can have multiple bodies in it. Now, so in this topo changer FB mesh, you can have like different things. So if you want to, so this was for like linear motion of the cylinder. So if you want to like run cases such as attach, detach, like if you want to run cases like linear valve motion, you can run it, you can use this mesh. If you want to run mixer FV mesh, so sometimes you have so you must have heard about this famous problem, that is stirring problem. You have a vessel and you have a mixture, like you have a stirrer, like you have a cylindrical body which is rotating and which is mixing. For those cases, you can use this mixture FV mesh. And then we have moving body top FV mesh, multi-mixer FV mesh. So you have to find like which is the perfect topological changing FV mesh for your problem. So for moving multiple moving cylinder in tandem, this multi-topo body FV mesh seems to be fine, less computational expensive, as well as like if you get the mesh right, the block mesh right, it will not give you, if you give you good stability, consistency, and leads to good conversions. So you have to like go through the block mesh, very dynamic mesh capabilities in also in the topology changes. After that, you can select it. And if you want to, let's say, uh, if you want to see what are the tutorial cases for mixed FB mesh, you can just copy its name and then do the grep command. And you can see this mixture FB mesh topology changes mesh methodology has been used in mixer vessel 2D, mixer 2D, and these are in uh, compressible and compressible solvers. And you can also do the same, like, so you can also always go to the application. You can always go to the application and you can see, do the same. Any solver you have here, you can also do and the grep command and see which are the solver which are compatible with the particular type of motion, like particular type of dynamic mesh methodology. Now we'll look into this. I think it is running from long. That is single cylinder dynamic mesh morphing case with very large amplitude. All right. Let's see. Not bad. It means what it just means that simulation is converging very well. So if you have a single structure, maybe mesh morphing with body fitted mesh is the best way to go. And if you have multiple structure, you have to go for different topological changes. Okay. Right. So now, we have you have seen. So now what about the motion of the body? So for motion, mesh motion, we have seen mesh motion for mesh morphing. Now there are library like solid body motion function. So these are the various motion that you can give to a solid body. That is for topology change. When you have a mesh region which is not changing and it is moving, like we saw in the previous problem that the cylinder and the associated square was moving independent of the other square, you have to use the solid body motion function. So it has constant velocity, it has graph harmonic oscillation, linear oscillation, rotating, and you can also give like tabular form of motion, prescribed motion you can also give. So these are the various mesh motion. Now, for now we have only seen like user defined motion or forced motion. What about the, if you want to give a free oscillation? So for example, you want to give a torsional or you want to give a damping, you want to give a torsional and uh, translational spring, and you want to do the free oscillation problem, that is VIV of a cylinder or uh, VIV of an aerofoil. So for that we have 6 degree of motion libraries, which I don't see here where they are. Let me see. Oh, post processing function objects. So versus point patch derived. Yeah. So as I told that this 6 degree of, so when we have a, whenever we have point fetch field, it means we are talking about the patch. So for example, in previous cases we have seen, for example, in these cases, we are giving a prescribed motion. But what if we want to give a free oscillation? We want to attach a spring in different direction, and we want to see how it moves, like how it moves with vortex shedding or under the influence of forces from the flow. So for that, we have this 6 degree of freedom rigid body motion library. You can, so this is it. Okay. So in this we have lot of, it has a lot of capabilities, like you can simulate a lot of, like 6 degree of freedom. You can simulate three translation, three rotational, like you can do a lot of things. So here you have 6 degree of freedom rigid body motion constraint, like in which direction you want to constrain the motion, and in restraint, 6 degree of freedom rigid body motion. Restraint means in which direction you want to control the motion. So for restraint you have to give damping or maybe stiffness to the spring. So these are like axial spring, linear spring, and spherical angular spring, and then you can also give tabulated axial spring data, like you can give non-linear spring also. So these are the libraries that you want to use if you want to like mm, if you want to use, if you want to simulate flow induced vibration. All right. Now what we want to, we want to see which are the tutorials that are already available that are using this 6 degree of freedom rigid body motion library. So for that, when we go to this derived, so we want to look for the type name. What is the type name for this? So the type name is, so we go to the .h file, we look for the type name, and when we go to the tutorials, then we go to tutorials, and in tutorials we do the same grep command -r. So we want to want to see which are the test cases which are using this point patch field motion library. So we have two cases. One is inter dy form, and one is wing motion. Wing motion 2D pimple dy form. All right. So that is an incompressible pimple dy form. Incompressible pimple dy form. Here we have wing motion. Okay. So here, so it is using snappy hex mesh. Okay. Because it is not simple to make a, because in cylinder we can make easily a block mesh, but for wing motion which has an aerofoil profile, it is not easy to make a block mesh. So people use snappy hex mesh. So this is simple form, but simple form is not of use. So we'll go to the pimple form and we'll see the dynamic mesh. So you see in dynamic FV mesh, it is using dynamic motion solver FV mesh. That is mesh morphing, you all know, and it is using displacement Laplacian. So it is similar to the mesh morphing that we have discussed. The thing that is changed is this point displacement. In point displacement, you can see that we have the boundary field is changed. We have boundary field which is wing, and in type we are describing 6 degree of freedom rigid body motion. We are describing mass, center of mass, moment of inertia, orientation of the body, acceleration, velocity, torque, and then in constraint we have fixed line, that is motion along a fixed line, and then we have fixed axis, that is rotation around a fixed axis. All right, then in restraint we have a vertical spring and we have a axial spring. All right, so you can use like 6 degree of freedom, you can use any kind of motion. Okay, so this is using, so what I did is in my previous mesh morphing, previous in my previous mesh morphing, this like in this case in which we have a mesh morphing and cylinder moving with hexahedral mesh, in that I just added, and just what I did is I just added, I took that point displacement file from the tutorial, and I did nothing. I just copy pasted it. All right. What I did is simply this. Let me just, this is point displacement. So these are 2 point displacement. So I did nothing. I just took this cylinder, this 6 degree of freedom library, and I simply copied it here. Nothing, just did this. Okay. Now, and then I ran it. Okay. So what I wanted to see the result. So I have already run it. I will not run it again because it takes time. So let's save some time for us. Then we'll just have a look how it runs. So the point is, in previous we were giving a prescribed motion. Now it is calculating the motion. That's simple as that. Just run it. Let's see how the pimple dy form looks when it run it. Acha, I think I have done some. So I have done some mistake in copy pasting. So let's do it again. Okay, let's save it. Remove this wing. Now run it. Center of mass is undefined in dictionary. Why it is saying so? Once again. It is always best to copy the case that was running so that if another case gives you any problem, then you can look back and what the previous version was. So it is always a good practice. Now let's run pimple dy form. Now it's running. So if you look, let's say, so with respect to other cases where there was prescribed motion, now in this case, this 6 degree of freedom rigid body motion is iteratively calculating the next position of the like mesh. What is the next position of mesh? So it is, you see, doing restrained vertical spring, this attached at this point, and then we have, so it is like doing extra calculation. So constraint fixed line one error is this, then it is doing another. So it is doing a lot of iteration to solve the 6 degree of freedom motion. Okay. So just wait a minute and keep it running. think one more, one more time step. Sometimes what happens is this 6 degree of freedom rigid body motion library convergence achieving convergence is very hard. So for cases where the forces are can be large, or like for example in initial transient simulation, forces can be very large. So in those cases, sometimes the 6 degree of freedom library is not able to come to a converged solution, converged updated displacement of velocity of the cylinder. So as I told you, first you find which the best methodology, and then you go ahead and keep. So yeah, so and then you go ahead and keep working in that, like to achieve the success for so simulating a problem. So you can see constrained fixed line error, then we have fixed axis angle this, and it is iterating eh, constraint like several times, and then it is calculating constraint force, constraint movement, center of mass. It is calculating linear velocity, angular velocity. It is calculating basically everything and then updating it. Now let's see how the results looks. You see, it is diverging. Yeah, yeah, it is giving us some trouble, I think. No, no, it is. No, it is okay. It is fine. Pressure is building on top and bottom, and to see whether flow over a bluff body is like at least the flow part, not the forces on the cylinder, but the flow part is doing okay or not, is to see that whether the vortex shedding has started or not, or like recirculation regions are forming or not. So you see, it is doing good. It is running well. So it means as you can now use prescribed motion as well as you can use 6 degree of freedom rigid body motion library to give a free vibration motion to the cylinders or any body. So for example, in this case, in this case, in this wing motion, it is giving rotation as well as the oscillation. So it is kind of pitching and plunging aerofoil, and it has a snappy X mesh. So it is using snappy. So you can go to the tutorial, like it uses the snappy X mesh, uses these three things, that is castellated mesh and snap and set. These are the three main three methods for the snappy X mesh: castellated mesh, snaps, and add layers. All right. So now, uh, I think now we have seen topology changes, and also now we have seen like mesh morphing and topology changes with the arbitrary mesh interface, or I'd say GGI. So with this, you can also, like, there are a lot of things. So if you want to see in tutorials, so arbitrary mesh interface is a little bit advanced version of the generalized grid interface that we have seen in this. So if you want to see which are the, so basically, arbitrary mesh interface is used for rotational things, more of a rotational thing. So if you want to look into which are the cases which are using arbitrary mesh interface, you can. Okay. So, I think we should search. So I click here. What happened? The patch name is should be this. Okay. Tutorials FE32 minus R. Mhm. You are not able to find AMI in this. Okay. So sometimes you are okay. So let's 1 second. Let's go to the source file. Dynamic mesh motion, rigid body motion function. So we have this is nothing parameters that. So you have to use another keyword if you want to find this. So let's go directly search the tutorials. So I think in incompressible, in simple DY form, axial turbine. I think so. In my open form version, I had some cases once. I think there are some things that are not there in form extend version. So I have for OpenFOAM 7 also. So OpenFOAM 7 is installed in where is it? OpenFOAM tutorials grep grep. Sorry. Okay, so I think form extend does not have arbitrary mesh interface. So things can change from version to version. So you have to. So you can see a lot of cases in the in OpenFOAM foundational version, that is OpenFOAM 7. So you can see there are multi-phase cases in compressible pimple form. So you have incompressible pimple form. All right. Uh, Incompressible pimple form. And I already case of mixer vessel 2D, uh which is where the dynamic mesh file is in constant. So if you look into here, it is using dynamic motion solver FB mesh, solid body motion rotor. Okay. It is solid body. It is using rotation, but it is not using 1 second. So it is like mesh morphing, but you can see it is using cyclic AMI. So it is using dynamic motion solver FB mesh, but the motion solver is solid body. So it is not displacement Laplacian or velocity Laplacian that you have seen for mesh morphing. It is just simple solid body motion. And solid body motion function is this. This is how the motion is prescribed. So I'll just show you the results. So for in these cases, for AMI cases, so AMI arbitrary mesh interface is not found in, I have not like searched as I've searched, it is not in form extent. It is in foundational version, and it is little bit, its capability are little bit advanced as compared to the generalized grid interface that we have seen in form extent. So we'll just quickly see the results. Somebody ask anything? You see, it is rotating. So for like, so for turbo machinery, rotating fans like propellers, compressors, for all these cases, the AMI is the best option that we have seen. Like you can see for turbo fans and all these things, you can use AMI. So you can see if you have a closer look, arbitrary mesh interface is moving, and like this is like as it is as the name suggests that the motion solver is only solid body. Okay. So this is arbitrary mesh interface. So I am just giving you introduction of the some of the cases, not the in depth. And also we have adaptive mesh refinement. So this is the case dam break with obstacle. We'll discuss this tomorrow when I teach you the immerse boundary methods and overset meshes. And in immerse boundary and overset meshes, we will go to some complex cases also. Now the one thing is that now we have seen that we can add or remove mesh. But when the mesh is deforming, we with like when the deformation is very large in some structures, in addition to addition and removal of meshes, we also want to like improve the quality of the meshes. All right. So to improve the quality of the meshes, we have a something called mesh kit solvers. So I have done some basic simulation in that, but that so this that is required when you have very complex body shapes of the structures and you have multiple structures and things are when very complex and you have no way another round, like you don't have uh like you can't use GGI, AMI, or you can't use immerse boundary or overset mesh. Then you have to go with the like remeshing and again improving the cells quality as the time progresses. So in those cases, the OpenFOAM provides mesh kit solvers. So you can again you can do grep command, but I know where it is, so I will not do it. So these are the where is motion smoother. So there are motion smoothers, motion solvers. Okay, one second, let me find. Mesh motion, I think. One second. Here, these are in mesh motion. Yeah, so these are the what they are called mesh quiet, or you can pronounce it. I don't know the exact pronunciation, but these are these solvers. So when you look into the .h file, it will tell you this can thin interface to mesquite mesh improvement library. So in addition to addition removal, it can also have like improve the quality of the mesh, and it also provides surface meshing smoothing capabilities. All right. So I have like changed. So what I did, I took that wing case, I convert that like the mesh morphing wing case tutorial that we had. I changed that for mesh morphing in cylinder, single cylinder, then change that to tutorial tetrahedral mesh in cylinders, and then we have topo changer heavy mesh. So what I finally did is I changed that case for the remeshing part. So I think you see remeshing. So here we have uh, wing motion 2D pimple DY form, and this is forced. So the only change that you have to do is that you have to change in dynamic mesh. So we want to see that with this mesh kit solver how the dynamic mesh looks. So this is how it looks. So we are using dynamic mesh libraries. Okay, you can always like also call these in control dict file also. You can also call these .so files in here, no problem. So we have dynamic FV mesh, that is dynamic topo FV mesh, that is topology of the mesh is changing. Like we are adding and removing cells. So in solver is Mesquite solver. So you see it has a lot of options. So each and every option is very important. And use point displacement, optional metrics, aspect ratio, like what is the aspect ratio of the mesh, and points function. There are a lot of things. Slip patches. These are the slip patches, and and these are the fixed value patches. So mesh will be solved around this patch. That is first cylinder, second cylinder, and so this is the wing motion. I have converted change these two for two cylinders, and I'm giving a prescribed motion here. Although you can also give like 6 degree of freedom, things like that. But for this case, you have to define everything in here because this is not like uh, a mesh is moving like in topo changer problem that we have seen. And here you have to define dynamic topo FE mesh threads, and there are a lot of parameters. So I tried running it, but it is diverging at some point. Okay, so uh it is running good, but after some time it is diverging. So for example, if I show you pimple, so the important part is to see the divergence, like why it is happening. To show you quickly the divergence part. So the thing is, the in unlike other cases, it is solving point motion. You see, the Mesquite solver is working here, solving point motion, initial residual. There it is improving, and it is again giving us the warning that minimum cell quality is this. So this here is all that is being done by this Mesquite solver to improve the cell quality, and and these are the mesh quality statistics, and then it moves to the another time step. All right. So let me show you what is the error that I'm getting. So we have to convert this to latest time. Okay, latest time done. If the mesh is fine, it will take time. But I can show you the case that I've already run. I think if it is there, if I find it. So yeah, so this is so in the dynamic. So in tutorials, we also have cases for the. So we also have cases of the meshes. This is move dynamic meshes. So in that this circular cylinder 3D is using Mesquite solvers. You see, so you should always go for the basic mesh motions tutorial cases. Go through the mesh motion tutorial cases, and then run these, and then try to implement this with the flow. So in mesh motion tutorials, this is the how the dynamic mesh dict file looks with the mesh morphing, their topology change, and Mesquite solvers. So let's just simply look how the motion is happening, how the like mesh is quality is being improved in this case. So this is only the mesh part. There is no flow in it. This is tutorial from the dynamic mesh. So see here it is. You see the cylinders is deforming this is very high deformation, but the Mesquite solver is making sure that the mesh quality is not decreasing. You see. So so you have to choose whether the Mesquite solver is good option for your problem or not. Let's see. So you see, Conan number mean is this and max is this, velocity magnitude this. So you see, it is diverging. So what I simply did is I took the wing case and simply tried using forced oscillation With Mesquite solver, topology changes every mesh. Topology changes every mesh and Mesquite solver for improving the cell quality. So you can see in these cases, it is running only till 0.05. After that, it is not able to run. Like so it is giving us core number problem. So to find a workaround this, you have to like go very deeper into the Mesquite solvers and also the mesh that we I'll show you the what kind of mesh that we are using here. So what I wanted to tell you is this. So this is okay. So I think this is due to the tetrahedral mesh. The problem can be due to the lot of reasons we have to find out. So in the first part, you can see the flow is almost, if you look at the velocity, it is not diverging that much. It is already diverged. So this is the tetrahedral mesh I've used. I think we should try go for hexahedral mesh and or like if we improve the parameters in the Mesquite solvers and topology changes, we can somehow reach to the which reach convergence. One more thing, I had one case I want just quickly show you 2 minutes. I think I have a case which was running successfully in this case. If I find it, I'll show you. I think this is it, you know. See. I don't think I have that case. It's okay. Like you can try it. I'll be giving you the test cases. You can try various permutation and combinations. So yeah, that's all from today. Tomorrow we'll discuss overset and immerse boundary method. So please, if you have any queries regarding your specific problem that we can discuss, like which is ALE is already there in OpenFOAM foundational version. The the test cases that I've shown you for mesh morphing, it is ALE. Uh, it is like installation is you have to go to the Google it installation. It is, but installation is not that hard. It is simple. The problem comes if we have a version of OpenFOAM already installed and you want to install form extent, then you can get some problem. Otherwise, it is okay. So I think immerse boundary method is very good. Like so, most of the cases, if you are able to like get with the interpolation problem that we'll discuss tomorrow, and I think it may be a good option for a lot of you guys to do structural analysis and for rigid body at least immerse boundary is very good. Any questions, please feel free to ask. No, IBM does not exist in foundation. It is not even available in the ESI version. It is only in form extent, and also in form extent IBM has some problems that it is not able to use 6 degree of body rigid body motion. It is not compatible with that. So for force motion, IBM is good to go. Given you are using dynamic refine mesh, like adaptive mesh refinement, it is okay. It is not in foundation version. It is not there. Even overset mesh is not there. A lot of things are not there. Any other question? Feel free to ask. Otherwise, if there are no question, uh, I'll be uploading these basic test cases in like by tomorrow. And tomorrow we'll discuss overset meshes and inverse boundary methods. Yeah, first to understand how it is capable, you just have to uh, so for to understand this, okay. So what you have, you go to the application and you are again do this grep command grep minus r and you find for the keyword dynamic mesh dot h dynamic fv mesh. So for all the solver which contains dynamic fv mesh dot h, they are capable of dynamic mesh capability. So you just go to application and do grep command with keyword dynamic fv mesh dot h. It will tell you. Similar to that, we have found the tutorials which have like specific dynamic mesh methodology. Similarly, you can do it. And mostly ICO DY form for incompressible in form extent, most of the time they have a keyword dy attached to it. For example, ICO dy form or pimple dy form, inter dy form, like this. Any more questions? So the thing is, if you are working on some specific problem in FSI, and if you want my advice, like which is the better methodology for my specific problem, you can also text me. Like I can at least tell you that which is the best methodology for your particular problem. And after that, you can go deep into that because even, for example, if you are using dynamic FV mesh motion solver or mesh kit solvers or using different methodology, like getting good results is also challenging in dynamic mesh. So at least it will save the time for you to decide which mesh is better for you, like which dynamic mesh is better for you. Okay, then I think it's enough for today. Tomorrow overset and immerse boundary method. That I think you should post on uh, that you should post on the group. Pratish will let you know. I don't think there will be any session. Today is the last session. But if you are working in porous media, you can access uh, Pratish library, which works on both thermal equilibrium and thermal non-equilibrium porous medias, and you can have access to his GitHub. So you like the libraries he has developed it, and they work fine in like foundational version. So Jamshed Moradi, if you want to work like want libraries which works very good in porous media, then you should go to the Pratish website, GitHub website. Okay, then thank you for joining. See you tomorrow at 7.